Hello again, this is Jerry Pinter, and welcome to our last part of our lecture on Chapter 1. In Part 4 of this lecture, we will be looking at the properties of LTI systems. So just a brief recap. A system is designated with just usually a box, and the system input is typically shown on the left with an arrow going in, and the output of the system is shown on the right here with an arrow going out. It's conventional, but not always used, to use the letter X for the input signal. So this is X of t going in. The system processes that signal, and it spits out the output signal Y of t. For a discrete time system, we have an input sequence X of n and an output sequence Y of n. So this is just a quick review of the basic notation that we will be using throughout this course for system notation. So there are various types of system architectures that we will encounter. For example, this one on the top here is an interconnection of two subsystems. There's system 1 here, followed by system 2 here, and you can see that they are connected in series. So this is called a serial or cascade interconnection. So the input of the entire system comes in over here. It goes through system 1. The output of system 1 then goes into the input of system 2, and then system 2 does its thing and spits out the output over here. In this middle picture here, this is a so-called parallel interconnection, where the two subsystems, system 1 and 2, are in parallel with each other. So here the input signal comes in over here, and notice it splits. It goes into both of these systems simultaneously, system 1 and system 2. Then the outputs of each of these subsystems are combined or added together here. That's the little summer or summation process here. And after they are added together, we get the overall output signal here. The one down here is the most general type of system architecture. This is sort of a series parallel interconnection where we've got actually four subsystems, 1, 2, 3, and 4, and you can see that 1 and 2 are in series, and they are in turn in parallel with system 3. Then their outputs are combined together and finally fed into system 4, and then here is the final output of this system. So we'll be encountering system architectures like this throughout the course. And sometimes we'll be using this cascade or series architecture, and other times we'll be using the parallel architecture. So here's a nice example that shows what cascaded or series systems can produce. And also, this is a good hint for homework problem 1.15. So problem number 15 in your first homework set has a problem very similar to this. It's a little bit different, but basically you're going to use the same technique here. So here's what the problem says. You're given a overall system here, S, which is in the blue box here. And system S consists of two subsystems, S1 and S2, and obviously they're connected in series like this. And their relations are, for S1 and S2, their input-output relationships are shown down here. So for example, system 1, which is this first subsystem here, the input X1 gets put through this subsystem, and what comes out is an output Y1 of n, which is equal to X1 of n plus 2 times X1 of n minus 1. So whatever's inside this yellow box here, it's doing this mathematical function on the input here. Okay, it's taking the input and it's adding twice the input, which is delayed by 1. Likewise, subsystem S2 has a little different characteristic. Its output is equal to its input, X2 of n, which is over here coming in, minus X2 of n minus 2. All right, so with this information, you're asked to determine the overall relation between the input X of n here and the output Y of n over here. So what does this entire system do? So the way to do this is, if we look at this, we can see that the output of the first system becomes the input of the second system. So that's sort of the key here. So I'm going to redraw our system up here like this. We have x1 of n going in to S1. We have y1 coming out, but that's equal to x2, which is the input of our second system, right? Because whatever comes out of S1 has to go into S2. And then finally, the output of S2 is our overall output that we're looking for. So let's write our relationship for system S2, which was given right here. So I repeated that. Y2 of n is equal to x2 of n minus x2 of n minus 2. And now what we're going to do is we're going to rename x2, which is the input of system 2, rename it y1, because remember that x2 and y1 are the same signal here. So this x2 here becomes y1, and this x2 here becomes y1. So we're just changing the name. But of course, y1 of n, we know what that is right here. It's x1 of n plus 2x1 of n minus 1. And then y1 of n minus 2, well, we know what that is because we know what y1 of n is. So all we have to do is delay it by 2. So this becomes x1 of n minus 2 plus 2 times x1 n minus 3. So notice this signal here or sequence is the same as this one, but the difference is it's been delayed by 2. So instead of n, we have n minus 2. Instead of n minus 1, we have n minus 3. Finally, with all of this written out like this, we can rename x1, which is the input of system S1. Well, let's just call that x because that's really what's going into S1 here. So all these x1s that you see up here, let's just call them x. And then finally, also the output here, y2 of n, which is what's coming out of the whole thing here, let's just rename that y. So, and then also we can combine all these terms. Remember there's brackets around here, so this minus sign gets distributed into both of these terms. But we can now, collect terms. We see there's an x of n. We have a 2x of n minus 1. That's this term. And let's see. Then we have a minus x of n minus 2, which is this term, and then a minus, remember this minus sign here got distributed in, minus 2x of n minus 3. So here's our final relationship for this overall system. So if you can follow what I did here, you should be able to do problem 1.15 in your homework. One of the most important system architectures is the feedback system interconnection. And this is something that we're going to look at in detail in Chapter 11. In fact, the entire Chapter 11 of your textbook is dedicated to feedback systems, and that'll be our last topic of the course. So this is just a quick introduction to this idea here. A feedback system, which by the way is also usually called a control system, the input, you can see it going over here, and it goes through, if we just kind of follow it through here, it goes through system 1, and that becomes the output. But the key thing here is this feedback loop. Notice the signal at the output up here is fed back through a subsystem here. This is sometimes called the feedback system. And its output goes back here and is added, sometimes subtracted, but in this case it's added to the input here, and which goes in, and then we go back around through the loop here. So this is called a feedback loop. And one of the neat things about a feedback system is that it has the ability to check its own output and make any adjustments that are needed. So it's for example, it can be a self-stabilizing system. It's used in amplifiers, tracking systems, autopilots, oscillators, and even there are natural feedback systems in population control, for example, in nature. So again, we'll look at this in more detail later on in the course, but just be aware that this is a very special and important system architecture. So this slide sort of summarizes 5 properties of systems, 5 important and pretty fundamental properties of systems. So let's start with the first one is called causality. A system is said to be causal if its output depends only on past and present input values. In other words, a causal system cannot look into the future. It can only look at what's happening right now or what has happened in the past. So most physical systems are causal, of course, because we don't have the ability to look into the future. Electronic circuits, for example, for the most part, are causal. Now, you may think that, well, wouldn't every system have to be causal? How is it possible to look into the future? Well, we can have a system that is acausal if its output depends on future input values. Now, how is that possible? Well, this happens all the time. If we're processing, for example, pre-recorded audio or video, or if we're going to do a rolling average of stock market data over a long period of time, one of the tricks here is at every given point, what you do is you remember these data points have already been recorded. And so if you want to know, if we're going to do some like rolling average, we might take this point here and the next 2 points in front of it and average them all together. So in this case, the system would be actually looking ahead in the data stream here. So it's not really, like breaking any fundamental laws of physics about cause and effect. This is an example of where we're dealing with data points in a sequence that already exist. Memory is another system property. A system has memory if its output depends on past or future values of the input. We usually think about memory as dealing with things that happen in the past, but technically if a system is looking ahead, like this example up here, then that system also has memory. A system is memoryless if its output depends only on present values of the input. One of the key system properties that we will deal with throughout this course is system stability. So a system is stable if small inputs produce non-diverging or finite outputs. And this is sort of a loose conceptual or qualitative definition of stability. We'll have more precise and quantitative ways to figure out stability later. But for right now, you can think of a stable system as one that just behaves well as long as the input to the system is not too large. So for example, think about this pendulum here. It's just a weight hanging on a string. If we give this pendulum just a tiny little nudge, like is shown here, the pendulum is well behaved. It's just going to kind of swing back and forth, and due to friction and air resistance and all that, eventually it'll come to a stop. So this is an example of a stable system. We'll deal with circuits later in the course that also are stable. All right. So what about an unstable system? Well, a system is unstable if small inputs produce diverging or infinite outputs. So remember our pendulum here. Well, think about if we made an inverted pendulum, and you can demonstrate this at home right now. If you take a stick or a pencil or something like that and balance it in your hand, all right, assuming it's perfectly balanced, all right, the question is it stable? Well, no, because if you were to just give this thing a little tiny tap with your other finger, this thing is going to fall down, right? It's not going to be stable. So this is an example. Microphone feedback. We'll deal with this again much later in the course in Chapter 11. But you've often heard microphones squealing. If the microphone is too close to the speaker. This is another example of an unstable system. So these 5 properties here will be investigated more in detail in homework 1, so you'll get a chance to to look at some examples of systems and try to figure out if they're causal or acausal, if they have memory, and if they're stable or unstable. Let's now turn to one of the most important topics of this course, and that is LTI systems. So another property of a system is linearity. And this is something that we're going to deal with in this course exclusively. We're going to deal only with linear systems. And of course, there are nonlinear systems as well, but they're much more difficult to deal with. So A system is linear if we can use superposition basically to add together inputs, especially if they're scaled. So what we're saying here is, let's suppose, or if we have a system here such that we put in x1, some input called x1. Let's say the system spits out an output which is called, we'll call it y1, okay? Now if we put a different input signal into this same system, for example x2, well the system is probably going to produce a different output, y2, all right? Now a linear system, what that means is that if we take these two input signals, x1 and x2, and we add them together, all right, and furthermore, if we scale each input, like we scale this one by some factor a, and we scale this input by some factor b, then the system output is just the sum of the scaled inputs. So notice that, x1 here produces y1, but it's been multiplied by a, so the output is multiplied by a. x2 produces output y2, and it has been scaled by some factor b, which shows up in the output. And notice since we're adding the two inputs here, the outputs are added together as well. So this is an example this is actually the definition of a linear system. The other important property is called time invariance. So a system is time invariant, which means doesn't change, right, with time. A system is time invariant if the system's properties are constant in time. In other words, a system doesn't drift and behave differently on, say, Friday than it did on Monday. So one way to think of this mathematically is if we have some sequence x of n that produces an output y of n, then if we delay our input x of n by some amount n naught, then the output will be the same, y, but the output will be delayed by the same amount. Okay, so in other words, if we delay the input by 5 days, then the system's not going to produce an output for the same delay, which would be 5 days. Okay, so this is time invariance. So if x of n goes into our system to produce y of n, then x of n minus n naught will produce the output y of n minus n naught. And there's a likewise expression here for continuous time systems. If x of t produces y of t, then x of t minus t naught, where t naught is some delay, produces the output y of t minus t naught. So this is time invariance. So in this course, what we are going to be dealing with are linear time invariant systems, or LTI systems. And this is the full definition of what an LTI system is. If x1 of t produces the output y1 of t, and if x2 of t produces the output y2 of t, then a times x1 of t minus t naught added to b times x2 of t naught, all right, for this input, the output of the system, notice, is scaled by a and b again. Here's y1 from x1, here's y2 from x2, and notice the output is delayed by t naught. So we have a y1 t minus t naught plus b y2 t minus t naught. So both properties are shown here. The system is showing linearity by simply adding these two inputs together, we get the outputs added together, and the system is showing time invariance because the inputs are delayed by some amount t naught, and therefore the outputs are delayed by the same amount t naught. So what we're going to do in the remainder of this part of the lecture is extremely important. We're going to do a series of activities that are progressively more challenging, and these activities are used to show the properties of linear time invariant systems. And so this is one of the key ideas of this first chapter of the course. So here's what you're given for this first set of activities. You're given this input signal here, x of t. If this is put into this system, then we get this output y of t. All right, so let's look at the input here. X of t is a triangular pulse, basically, right, of 5 seconds in duration. So if this triangular pulse goes into the system produces an output which is this triangular pulse. So it looks kind of the same, but obviously it's been stretched out to 10 seconds, all right? So this is all you're given right here, okay, about this system. This is all you know. So there's 3 different activities here. The first one, which is probably the easiest one to do, is what would happen if this input right here was put into this system. In other words, make a sketch of the output for this input. The next problem is also fairly straightforward, but a little more difficult. What would happen now if the input looks like this? So it's 2 triangular pulses right next to each other. What would the output look like this? All right, and in order to solve this, think about linearity and think about time invariance, right? This is an LTI system. The last one is what would for this input, all right, where we have a signal that looks like this, what would the output of this system look like? So in all cases, this is the same system. All 3 of these activities here are using this system up here. So go ahead and pause the video here and see if you can figure out how to do these. All right, let's go through these 3 activities that you were just given one at a time. So the first one was what happens if this input is put into the system? Well, this one is fairly straightforward. We know that this first signal right here, this first input signal, is going to produce exactly this. So that's what's shown here from 0 to 10. Now notice at 10 seconds, the system sees another one of these triangular pulses. And they're identical, right? The only difference between them is, one happens 10 seconds after the other. So at 10 seconds, this second one goes in and is going to produce another one of these outputs, but of course it's going to start at 10 seconds because that's when it went in. So that's the time invariance part of the LTI system. All right, so here's what the output would look like for the first one. Let's move on to the next example. All right, so the second activity was what would happen if the input looked like this signal? Well, this is a little different because what happens here is the first signal, let's just take this first triangular pulse here from 0 to 5 seconds. We know it's going to produce this output here. So, the output is going to go up, and then I'm showing the dotted lines here because the system is going to produce basically this triangle right here, which is the same as this one up here, and that comes from this input. But now something happens at 5 seconds. At 5 seconds, the system sees another triangular pulse starting. So the system output is going to produce another one of these triangles, this one shown here. All right, so you can see there's 2 triangles shown here, but they're overlapped. Why? Because the output takes 10 seconds to complete, and the next input is coming before, it's coming at 5 seconds. So the output of the system, we have to use superposition now. This is linearity. We have to simply add these 2 triangles together to get the solid line right here. So this would be the output of that system, of this input right here. Okay, the last one for this particular activity, this was the input. It was a positive triangular pulse, followed immediately by a negative triangular pulse. So we know the positive triangular pulse from the first 5 seconds produces this output here. So that's shown here with a dotted line going over to 10 seconds. You can, again, kind of think of it like a triangle there. Now, what happens at 5 seconds? Well, now the system sees an inverted triangle. Well, this is just the same as this one up here, except it's multiplied by -1. And the system is linear. So it's going to produce an inverted triangle like this that points down. But of course it starts at 5 seconds because the inverted triangle here started at 5 seconds. So we would get something like this dotted line here followed by this solid line here. Now for the times between 5 and 10, we have 2 overlapping signals. So we have to add them together. This is linearity. Remember, it's superposition. So adding these 2 dotted lines together, you will get this solid line here. So the answer to this last one, which was probably the most difficult of the three, is this solid line shaped waveform shown like this, or signal. All right, so notice for all of these activities, we didn't have to use any math per se, and we just had to sort of sketch out what it would look like, for each of the inputs. It helped to make a sketch of the outputs, because sometimes we have to add together different outputs. All right, let's move on to another type of activity here. So in this last set of activities for the chapter, again, this is extremely important that you understand and learn how to do this type of thing, because this tells us quite a bit about the properties of LTI systems. So in this one, we've got, we're given that this input sequence, x of n, now this is a discrete time system, obviously. The input, if the input is two ones, all right, these are two unit samples or two delta functions, then the output of the system is a 3, a 2, and a 1. Okay, so that's all you're given about this system. So what would happen if the input was this signal shown here? All right, so this is the easiest one of all of these. All right, so do that one first, and then the next one is what would happen for this input here, where you have 4 ones in a row. All right, this is a little more tricky than this one, because there's going to be some overlap of the outputs, and you're going to have to add them together. Then there's this one here. The input now goes 1, 2, 1. So how do you deal with this when all you know is this up here produces this here? Well, there's a trick here, and I show you the hint here. You can write this input signal as the sum of a couple of these. Now they might be overlapped, remember, okay? And then finally, this is a really challenging one. If you're really up for the task, see if you could figure out what the output of this system would be for just a single one here. How do you do that? Well, I gave you a hint here. Okay, so again, go ahead and pause the video here and see if you can figure out the outputs to these 4 inputs shown over here. Let's go ahead and go through our activities one at a time at the solutions here. So the first one, the input was 2 1s followed by 2 0s and then 2 2s. So obviously the 2 1s, that's the easy part. We know it produces a 3, 2, 1. So that's shown here, 3, 2, and 1. Now at time, this is 0, 1, 2, 3. So when n is equal to 4, the system sees a pair of 2s coming in. Well, this is just twice as big as this one, right? This is just scaled by a factor of 2, and it's a linear system, so the output will be scaled by a factor of 2. So we're going to get a 6, a 4, and a 2, and notice it starts here when n is equal to 4, because that's when this input comes in. All right, so this is the solution to the first one. So again, if you didn't get this, make sure that you understand and know how to do this before we go on to the next one. All right, so this next one is a little more tricky. Notice we've got a 1, 1 followed by another 1, 1. So we know that the 1 and the 1, which is exactly this here, produces a 3, 2, 1. So here's another kind of way you can do this. I'm going to write 3, 2, 1 as my sequence, just as I showed here. But notice when n is equal to 3, the system sees another 1, 1. So it sees another one of these. And we know that produces a 3, 2, 1. So we get another 3, 2, 1. But this one, of course, starts when n is equal to 2 here. So this is n equals 0, 1, 2. So there's overlap. The first 3, 2, 1 overlaps with the bottom 3, 2, 1. And therefore we can add these together now. So we have 3, 2, and here we have 4, 2, and 1. So our final output of our system looks like this: a 3, 2, 4, 2, and 1. Okay, so this used a combination of linearity and also time invariance to handle this delayed part right here. The second half of the input was delayed by 2, so we just moved this thing, this 3, 2, 1 is moved over twice. Okay, so again, hopefully this will become apparent. If you didn't get it right, make sure you understand how to do this. Okay, the next one is a little bit more challenging. The input was a 1, a 2, and a 1, which of course doesn't look anything like this, like a 1, 1, which is what we need to get. So the hint here said write the input x of n as a sum of the input at the top page. So notice that 1, 2, 1 is the same as a 1, 1, which is this, plus another 1, 1 that's been delayed by 1. Okay, so if I add this sequence here to this sequence here, I get what we're looking for. So we know how to handle these guys, right? This first one here produces 3, 2, 1, and the next one, here's a 1, 1. Well, it also produces 3, 2, 1, but it's just been, notice it's delayed over by 1. So I have to line it up here accordingly. Here's the 3, 2, 1 from this first term here, and then the second term here produces this 3, 2, 1 like this. Now I can add them up. We have 3, 5, 3, and 1. And so our output looks like this, a 3, a 5, a 3, and a 1. All right, so this is our last activity, and this was, I kind of warned you, this was the challenge problem. If you could figure this out, then you're doing pretty good, because this is not a simple solution by any means. We're asked to find the output for this single impulse here when all we know is that 2 of these impulses produces 3, 2, 1. So how do we make this impulse a sum or a scaled sum of a bunch of these? Well, there's a trick here. What we can do is we can say that this, our input, that single 1 there, is equal to a 1, 1 plus now here's a 1, 1, but it's pointing down. That's a negative 1, a negative 1, negative 1, and it's delayed by 1, plus up 1, 1, delayed again, plus down 1, 1, delayed again. So notice that if we just keep adding these together, and by the way, this just keeps going on, what happens is this first one here remains, and there it is right there. That's what we want. But what happens to this one here? Well, it's canceled by this one, this one right here, right? This positive one here gets canceled by this negative one here. So it goes away, all right? But now we have a negative 1 at n equal 2. Well, that's canceled by this positive 1 on the next one at n equal 2. But then we're left with a 1 at n equal 3. Well, that's canceled by this negative 1 at n equal 3, and so on and so forth. So as long as this thing keeps on going, every one of these gets canceled out except for the first one, which is this. Now, why did we do this? Well, we know how to handle all of these terms here because they look just like this. They're either this version here, or they're just flipped, which means we just have a -1. So this first term here produces a 3, 2, 1. The next term here produces, now it's delayed, so it produces a 0, -3, -2, -1. It's negative because the input is negative. And then the next one here is 0, 0, 3, 2, 1. The next one, 0, 0, 0, -3, 2, 1. And this, again, this keeps on going. So what we can do here is write this out. So this first term here is 3, 2, 1, and then I just put a bunch of zeros after it. The next one is delayed over 1. So it's a 0 with a -3, -2, -1, and a bunch of zeros. And then the next one is positive 3, 2, 1. But every time we go to the next term, it's delayed one more placeholder to the right. So we end up with a pattern like this. And we can stop now because we can kind of see what's going to happen. So let's go ahead and add up our columns here. So the first column is a 3. The next column, 2 minus 3, is -1. And then 1 minus 2 is 2. I forgot the 3. 1 minus 2 plus 3 is 2. -1 plus 2 minus 3 is -2. And here we keep going. Now it's 1 minus 2 and 3 is +2. So you can see what happens here. We start with a 3 and then a -1. But after that, it's 2 minus 2, 2 minus 2, 2 minus 2, and this would just repeat forever. So believe it or not, after all that, this is the output. This is what it would look like. It would spit out a 3, and then a minus 1, and then it would alternate 2, negative 2, 2, negative 2, and it would just keep going forever and ever. So that's the final answer here. This one obviously was a little bit more challenging. It took some creativity to kind of break apart this input here into a bunch of versions of what we're looking for up here, but it is doable. Okay, that is it for this chapter, and we will continue on with our course with Chapter 2 next. Goodbye.